In this video, we are going to look at a specific relationship between the electric field and the electric potential. So to start to explore that, I want to look at a particular situation in which physically we have what is usually called a charged plate. That is to say, you take some sort of metal or some sort of conducting material, would be better to say, in the shape of just a sheet or a plane, and you take two of them, I should say, and you charge one of them positively and the other negatively. I don't think I've drawn this very well. 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. We need as many positive charges as negative charges to make this work. So we know what the electric field is going to look like in this gap, and what I'm going to assume is that this gap is actually really small. I can't draw it really small because then it wouldn't make any sense. I'm going to assume that this gap, that is to say the distance d here, is really small in comparison with the length of these things, or the height in this orientation. Again, so just imagine that this is really close together. And if I do that, it's going to be my contention that throughout most of this, the electric field looks like this. Go straight across. We know that the electric field is going to start on positive charges and end on negative charges. And what we have also seen is there's going to be a lot of cancellation due to symmetrically arranged charges. For instance, this charge and this charge along this line are going to produce electric fields that, this charge will produce one that looks like this. This charge will produce one that looks like this. And there's going to be cancellation in this sense in the up and down direction, which is going to leave us with this net field going to the right. We've seen that a lot. I'm going to assume that that explanation is good enough because we've seen it many times. And what I'm going to find is that that will hold as long as I'm towards the middle of this thing, right? If I start getting towards the outside, right, well, this charge will have a field out here that'll look like this. But there is no charge to cancel that field, right? And so towards the edge of this thing, I'm going to start getting electric fields that curve around like this. What we're going to do for the majority of the work we do in this course is ignore those so-called edge effects. That is to say, we're going to assume that this distance is really small and that we're staying pretty much close to the middle of this thing. If I do that, then I get this electric field, which is really uniform. It's uniform in magnitude and it's uniform in direction. Okay, so we're going to assume that I'm staying really close and that these little curved lines at the end are not going to come into the region in which I'm looking. Okay, if I do that, now, what do I have here? Well, I know a couple things. I know that electric field lines point in the direction of decreasing electric potential, which means that the potential over here is higher than the potential over here, right? Electric field lines point in the direction of decreasing potential. Fair enough. Now, of course, I can measure the voltage across these two plates, and that is the right language. I measure the voltage across. Remember, the electric potential changes as a function of space. It is one value over here, one value over here, so on and so forth. I guess we should do that in frame. One value over here, one value over here. So between these 2 points, or lines in this case, but this point in the x direction, this point in the x direction, there is some difference in potential, electric potential. What I'm going to do is, because I can set my 0 point wherever I can, remember, the potential is based on potential energy, and that ability to set your 0 point wherever you want to comes right along with it. So what if I had to say, okay, over here, this is going to be 0 volts, and that means as I go to the left, I'm climbing up the hill, as it were. I'm increasing in potential because I'm going opposite the field lines. Let's say for this particular system, and this is just a number I'm pulling out of the hat, I'm going to say I get 10 volts over here, right? So what I'm saying, the correct language is the potential difference between these charges and these charges is 10 volts. So we see as I move across that my voltage goes down. So I can arbitrarily draw in, let me see, about there. I think that'll work. I can arbitrarily draw in it's not arbitrarily, sorry. Somewhat, because I'm choosing how many lines I draw in. But let me draw in these lines. And what's going on here is if I have a uniform field, if the field is truly uniform in magnitude and direction, I'm assuming it is, then the decrease in potential should also be uniform. In other words, I'm going down a straight hill here. I'm uniformly dropping in potential. And so for this particular system, that actually just boils down to dividing up this space into equal distances and then seeing how the potential drops. So if I'm dropping 10 volts as I go down, that means over here at this line of positive charges, I've got a potential of 10 volts. And the way I've drawn it, it looks like as I move across the space to this line, I've got 8 volts there, and then here 6 volts, and then here 4 volts, and I left out a line. There's a line there. We'll say that that's 2 volts. And then that brings me down over here to 0 volts. So to be complete, I'll put 10 volts there. So see what's happening. If I measure the potential, and of course, if I'm measuring potential, I always have to reference some point. If you ask how tall you are, right, you are implicitly referencing your feet. I'm 6 feet tall. That means my head is 6 feet above my feet. If it wouldn't make any sense if someone was like, how tall are you? I'm like, well, 8 inches. Well, what are you talking about? I'm referencing my shoulders, right? Top of my head is about 8 inches above my shoulders. That doesn't make any sense. Here, it doesn't make any sense to reference any point but 0 volts. So I have assigned this point to be 0. I'm referencing everything else. That means if I measure the potential between 0 volts and this line, I get 8 volts. 0 volts, and this line I get 6 volts, and 4 volts, and 2 volts. Do you see how the analogy here in gravity is that I'm going downhill? This hill is 10 volts high, and as I walk down the hill, that is with the field lines, I get down to 8 volts, and then 6 volts, and then 4 volts, and then 2 volts, and finally, I'm at the bottom of my hill, 0 volts. All right, fair enough. That leads us to a really interesting way to characterize the electric field. The electric field here then becomes just simply delta V over, I'm going to write it this way, delta X. So this is what I want you to be familiar with, right? And in this particular case, that I can make that even simpler, V over D, right? Where I can leave off the deltas as long as I understand that this is distance D, and I'm measuring this voltage, right? Whatever distance goes here, I'm measuring the voltage between these points. So in this case, I've called this whole distance D. So I measure the point from here to here, and I get 10 volts over however many meters that is. Of course, this works just as well if you use a different distance here. Say if I used this distance between 0 volts and the 8 volt line. It's a different distance than D. I would put 8 volts over whatever that distance is, and I should get the same answer because that's how this particular system works. So hang on to this equation. This is not a general equation. This is the equation for this particular system, but as it turns out, we see this system a lot. A uniform electric field in between 2 charged plates. This one is a little bit more general. By convention, we do a lot of things by convention in electricity. And we've seen some conventions involving signs like the electric field direction, all that good stuff. I'm going to put a negative sign here. That's again by convention. That's to be complete. Very often I would ignore the negative sign and just look for something like a magnitude. But this is a general equation. That is to say, if I can figure out in any system how the potential is changing as a function of space, right? As I move through space, how that potential changes, then I can determine the electric field. And that becomes, in this situation, a really, really simple. So this is a very special, simple case of this general formula. Because usually the change in voltage and the change in distance is not linear. In this case it is, because I've got this uniform field. But if I had a non-uniform field, that wouldn't work. But in this case, it works to be really easy. I just get V over D. Of course, that you can rearrange that to say that the voltage is equal to DE or ED, however you want to say it. Okay. Now, looking at this leads to actually some alternative units for the electric field. Remember from the previous work we did, I had this. Electric field is equal to force per unit charge, right? Units here are newtons per coulomb. Here, I've got this electric field. If I look at the units here, V over D, that is a volt per meter. As it turns out, both of these are good ways to characterize the electric field. You can turn one into the other if you're able to unpack all this stuff. Remember, we in almost any unit you see, there's some stuff packed in there. In fact, the only thing here that doesn't have, that is not representative of a bunch of other units is the meters. Volt has a bunch of stuff wrapped up in it. We know Newton does, Coulomb does also. We're not going to worry about unpacking that, but you can turn one into the other. But either of these units work just fine for the electric field.